Okay, to introduce you the Rostand algorithm, let's have a quick recall of diffusion. Okay, what do I mean by diffusion on the data set, or what is the general setup, which is not specific for this database or this problem, it is generic. Okay, so I give you n points in R-dimensional space. Okay, and then you can construct an affinity graph. And this affinity graph can be constructed by many different ways. For example, you can use complete graph. You connect all points. You can use KNN, K nearest neighbors. You can use epsilon ball. If 2 points are within epsilon distance, then you link them. There are several different ways you can construct an affinity graph. Now, let's construct one. Once you have the graph, you want to assign affinity. And how to assign affinity? Today, we'll just focus on this very simple affinity. We will not design it. We use the Gaussian kernel, saying that we have the distance in between xi and xj. Then we just put some epsilon, which is the bandwidth, and we take exponential, which means that if 2 points are very close with very small distance, then the affinity will be high. But if the distance is large, 2 points are far away, then the affinity will be low. So this metric is actually very, very important. How to design a metric plays the critical role. Yes?
Your graph is somehow complete.
Yep, it doesn't need to be complete.
Okay.
Yeah, but so you can say it's
so the distance is from P. You could keep P-dimensional Euclidean space.
Yes, you can use Euclidean distance. For example, you can say E of xi, xj is just the Euclidean distance. Or you can do something which we will introduce in a bit. We will take covariance matrix to design a metric so that we can get intrinsic information. That will be another thing which we'll talk about. And bandwidth selection, this epsilon is actually also the key. And how to choose epsilon plays also a critical role in the whole game. But today I will skip it. I have to skip it, otherwise I have too many information. Okay, but if you are interested in it, you can read some paper I have published in information theory, in transactional information theory last year. And from this affinity graph, you can build up an affinity matrix, which is an n by n matrix. And if ij is an h, then you put omega ij. Okay, otherwise you put 0. And then you can construct a degree matrix, which is a diagonal matrix, so that the ith diagonal entry is just the row sum of the W matrix, affinity matrix. Once you have D and the W, you can construct a transition matrix on the data set. Yes, it's a Markov process. The transition matrix of a Markov process, D inverse W, which is row sum up to 1. Okay, so that is what you have from the data. And once you have this transition matrix, what is diffusion? Then it becomes very trivial, right? You have D inverse W. If you apply to V, evaluate I's component, you see it is a random process. And from this random process, you can simply apply eigendecomposition. Okay, but you need to be careful about eigendecomposition, because if you construct the affinity graph using complete graph or epsilon ball, then W is symmetric. But if you use KNN, W may not be symmetric. And the D inverse W may not be diagonalizable. Okay, so let's assume it's diagonalizable and forget about this small technical detail. Then once you have the eigendecomposition, you can take some diffusion time t and define a diffusion map. And the diffusion map is defined by taking eigenvalues raised to power t and use the ith entry of the first q eigenvectors, right eigenvectors actually. And then you get new points in q-dimensional space.
Sorry, what
yep.
T? T
is the diffusion time. How fast you diffuse. How much time you diffuse.
It's just the power of T.
Power of T.
Okay.
It's power.
You get lambda and then just
Yes.
the power.
Yes, exactly.
Okay.
Yeah. And you can show that D inverse W, okay, suppose the kernel, because we work with Gaussian kernel, so it is always positive definite. By Boltzmann theory, eigenvalues are always positive and bounded by 1. Yeah. And so this guy can be well defined. You don't need to worry about negative value, taking power, you'll get complex values or something. No, it's not what you need to worry about. Every fraction works. And usually you can consider more general kernels like positive definite kernels. There are many you can choose, but we choose just use Gaussian. Okay, once we get the embedded point, then you can consider the difference and so on. That would be the diffusion distance, which we'll encounter in a bit. But no matter what, the whole process allows you to visualize high-dimensional data, achieve dimension reduction, or recover nonlinear geometry.
You start from the second eigenvalue.
Yes. Why? Because the first eigenvalue is always 1. Right? And you can see that T inverse W is just 1. So everything, all the eigenvalues will be bounded. And the second eigenvalue is actually controlled by triggers inequality, which tells you the connectivity of the manifold, of the data set. And we don't need to worry about that in our setup.
Okay, but now the diffusion map, okay, the dimension is originally P.
Yes.
But how did you choose Q?
Oh, that's a very good question. I can tell you, so far, there is no theoretical guarantee. Okay, the only thing we know is, in some cases, if the data set have a very good behavior, then you can choose Q to be much smaller than P, so that you can recover everything. But in practice, it may not always happen. Okay, and you may never be able to reduce the dimension. For example, you will see that you have a Klein bottle, and Klein bottle is embedded in 4-dimensional space only. It cannot be embedded in any Euclidean space with dimension lower than 4. Then when you apply diffusion map, there's no hope you can get a dimension reduction. There's no hope. You just cannot. The minimal dimension you need is 4. There's a topological constraint. So in practice, how to choose the dimension Q to guarantee the embedding or guarantee almost isometrical recovery of the manifold so they can recover nonlinear geometry. So far, it is not known. We only know that for a given epsilon, a tolerate error is given. Okay, then you always can find finite eigenfunctions of the Laplace-Beltrami operator so that the embedding is almost isometric up to epsilon. That is a result proved in 2016. Okay, but what is this dimension? This dimension can be super large. For example, you think about a manifold S1 times epsilon S1. It's a 2-dimensional manifold. You sample points from it. How many points, how many dimensions, how many eigenfunctions do you need to recover this manifold? 1 over epsilon squared. That's very difficult. Okay, so there must be some topological conditions or geometrical conditions that we need, we can have to guarantee the dimension reduction, but that is an open question to my knowledge.
So you don't know a priori the best?
No, we don't know. You need to do try and error. So in this sense, we do not fully understand this kind of diffusion map algorithm. We don't, not yet. But we have known quite a lot, but just some critical parts are still missing.
Okay, then the other question is, what's the difference from the standard principal component analysis? They do something similar, but
They are very different. I can show you one example. For example, you can consider this is RP. Can you consider an interval? This is a set. You call this I to be the one-dimensional manifold, and you sample points from it. Okay, and this is in RP. Okay, you run PCA. The first principal component will allow you to recover it isometrically. But if you run diffusion map, which I haven't mentioned, but later on you will see that the diffusion map or the algorithm I will mention will give you a convergence to the Laplace-Beltrami operator with the Neumann boundary condition. So right now, if I give you okay, and F, hello, sorry, Neumann boundary condition in this case, what will you get? You'll get sine and cosine. Okay, so if you use sine and cosine to do the embedding, what do you get? You get curvy embedding, curvy curve. So it's very different from PCA. And if you
have the direction.
Yeah. And if you want to recover or isometrically recover it, you need many, many eigenvalues. And that is actually kind of it reduced to a Fourier series. I give you a 0-1 interval. How many how many Fourier modes do you need to recover that function? Well, it's not that simple. Okay, good. And there have been many works in this direction trying to understand what's going on. But as I told you, we still have gaps.
But it seems they're quite. I mean, these 20 years it started. I mean,
Yes, it has been.
The algorithm was proposed 1994.
Oh no. This is published in GAFA. This is spectral embedding theory that tells you that if I give you Laplace-Beltrami operator and give you eigenfunctions and eigenvalues of Laplace-Beltrami operator, how can you recover the manifold using spectral embedding? And the first algorithm in this direction is actually 2003. In that paper, it's called eigenmap, where time is 0. They do not consider diffusion time. So you cannot get almost isometric result. Koifman, Lafont, in 2006, that's called diffusion map, which introduces the time, which gives you the chance to achieve isometric embedding. Okay, and the true isometric embedding was kind of almost isometric embedding was published in 2016. That's what I mentioned. You can use finite eigenfunctions to achieve epsilon, any epsilon positive, epsilon tolerable error. It's a portage.
So okay, this is the, I mean, okay, you constructed a map already,
Yep.
but this, I mean, converge to the real one t goes to 0, something like that, or
Yep, right. T will goes to 0. In this GAFA's paper, when the error depends on the diffusion time. And this is very obvious, right? Because locally, if you diffuse too much time, then the local geometry will be disturbed so that you cannot see local information. So you cannot diffuse too much. You need to diffuse very, very shortly. But how short is short? It impacts how isometric embedding is.
but do you get the map only at the point I?
Oh no. The embedding or the embedding or the convergence of this kind of map is on a spatial sense. That is,
I know, but you basically the map should be defined on R T.
yeah. Yes. This is the xi, the i's point,
Yes.
right? And right now, i's point is in p-dimensional space. So the map is defined on the manifold which is embedded in p-dimensional space.
I know, but
Yes.
this one only gives the information on the page.
Yes, on those points, yes. So the result is asymptotic when you have more and more points.
Okay.
You will sample everywhere on the manifold. If you only have, yes, if you only have finite points, then you need to do the extrapolation. Okay, which we will introduce in a bit. That is, if you only have n points on the manifold, then the embedding this UL will converge to the true eigenfunctions of the Laplace-Beltrami operator via extrapolation. You fill in everywhere.
So theoretically, it's guaranteed when you have a plenty of,
More and more points. Yes.
Points. Maybe also the order. You have the order of convergence was up.
Yes. I will show you one version, which is a variation of diffusion map for computational purpose later. Yeah, but the same ideas hold for generic algorithms. Okay.